Yeah, so I think let us start from the same uh, content which we were talking about in the last lecture. I hope my voice is clear.
Yes, sir. Yes.
Okay. So in the last lecture, we had seen the, I think, design rules, layout design rules we had seen, and we understood that these design rules specify the minimum dimensions for each layer that you draw in the layout. So for example, we had minimum design rules for poly lines, then maybe contacts, via contacts, the diffusion regions, or the spacing between the two regions or two lines, then surround rules, right? And then we also saw how to draw the layout of NMOS and PMOS, right? Now let us try to draw the same layout on a software. So I'll provide this software to you. In fact, this software was from Tanner. So the software's name is L-Edit. Okay. So I have a student version copy of it, so I'll share it with you. Though Tanner is now acquired by Mentor, so you may not find this on the web, or maybe you can find also. So this software you don't need to install. Just open the, unzip the files. Okay. Maybe some sort of unzip, zip file I'll share with you, and then you have to unzip it. And in the folders you will find two things. That is the foundries you will find where the extract definitions and all will be provided. So two foundries are mentioned here. For example, Moses and Orbit, right? So Moses is a foundry. I have, I think, opened this website of Moses. If you go to moses.com, so you will find it's a foundry, Moses. Okay. And in fact, Wikipedia also, you can see Moses stands for Metal Oxide Semiconductor Implementation Service. Okay. And this provides MOS chip design rules and related services that enable universities, government agencies, research institutes, and business to prototype chips efficiently and cost effectively. Okay. And this service has delivered more than 60,000 integrated circuit designs so far. Right. So Moses is a foundry. So similarly, we have another foundry called Orbit. So they have given some rules for extracting the parasitics from the layout, and also the layout design rules one has to follow. In fact, whenever we are trying to extract the parasitics, we'll select any of these files from the foundry. So depending upon whatever process technology we are working on, so we'll utilize the relevant technology file so that the parasitics can be extracted with respect to whatever process technology we are trying to extract for, right? So for example, this Morbin 20, this is for 2 micron technology. Similarly, Morbin 12 here. So this is for Morbin 12 is for 1.2 micron technology. Similarly, we have others also, MHP 05, that is 0.5 micron technology. So whatever process technology we are aiming, we will try to use the same process technology extract definition file to extract the parasitics. Then apart from this, you will also find executable file here, L-edit executable file. This is an application file. So first step is you will have to just right click on it, and then go to properties of this file and compatibility. And in this compatibility, you will select run this program in compatibility mode for Windows 7. Okay. So this option you will have to check If you are using Windows 10 or maybe Windows 7, you will select this option, that is run this program in compatibility mode for Windows 7. Otherwise, it may not run. So I'm using Windows 10 on my PC. So I have to select again, even if you are using Windows 7 or Windows 8, you'll have to select this option. Then the color mode. So here, in fact, it will ask later also. So you will select the reduce color mode. Okay. Maybe 16-bit is okay. So you'll select this. So even if you don't select this, it will ask you later. And then you say OK. And then one has to double click on the same file edit. So once you double click it, so you will need to run it in administrator mode. So once you run this, you get this window, right? Edit student version. Okay. So I click OK here. Then it says it needs a 256 color palette. So you say yes, and the layout window opens up. Okay. So here you do not have to make any settings. If you are seeing this color palette, I mean, this color palette should be visible to you. If it is not visible, then you need to go to this file, replace setup. You press this, replace setup, click, and then browse and go to the same Moses folder, yeah, which was present in the same software folder, Moses folder, and select any of these. So for example, you are working on 2 micron technology, you can select Marban 20, 1.2, 12, right? So any of these, let us say we are working on 2 micron technology, we'll select Marban 20, okay? So this you have to perform only when you are not seeing anything in this window here, and you're also not seeing the color palettes over here, right? So this color palettes, this region here on the left side, this represents all the layers which we will utilize for drawing the layout. So for example, the red one here, so if I keep my mouse pointer here on this, it says it is a poly. Then the green one is active, right? Similarly, I bring down my pointer to blue one, it says metal 1. Similarly, metal 2, okay, I'm just bringing it down. Metal 3, this is via end well, right? Then we have end select, then P select, okay? Then poly contact, active contact, vias, yeah, and then many other layers are present here. So let us utilize these to create a layout, okay? So for drawing the layout, you need to check this box also, right? So this box, that is, it will help you in drawing only the boxes, right? So these are actually the shapes which you can draw. So I always normally select this one. So I don't select all these. My job is normally completed if I select this one. So I always select this one. And then let us say we want to draw a PMOS first, okay? So for PMOS or for any MOS, you will always assume that this background, okay, this white background, this is a P-type semiconductor, okay? As mentioned in the previous lecture, that the background is always P-type semiconductor. And to draw a PMOS in P-type semiconductor, you will need N well, okay? Okay, just a second. Yeah, so background is P-type semiconductor, and if I want to draw a PMOS in a P-type semiconductor, I would need a N well. So I'll again come back here to this color palette on the left side, and I will look for N well. Okay, so here is my N well. So I'll click on it, and then I'll bring my mouse pointer here, and I will click, hold, and drag this. And then leave it, maybe a little bit smaller. So my N well is created. Okay, now I have drawn it very big. I mean, I will make it big, and I'll not go by the dimensions, exact dimensions. I'll try to keep things big so that there are no DRC errors in my layout. But you will not follow this thing. You have to optimize your layout. So obviously you'll have to push the technology to the limit. That is, depending on your transistor width and length, you will select the green active regions and then the N-well regions and the N-select null regions. So all these boxes that you will draw, you will try to draw by matching your transistor dimensions, right? So first of all, you will draw the layout on the paper by considering minimum possible dimension, and then come on to this window on layout editor to draw the final layout, because then only your transistor will be optimum transistor, an efficient transistor. Okay, the transistor which I am drawing, just it's a arbitrarily transistor, so it may not be very efficient. Okay, so N-well I have drawn. Then in N-well I'll have to draw a P-select region for PMOS. So I'll just again find P-select. So its P-select is found here. Okay, this one is P-select. I click on it again and I bring it, the pointer here, mouse pointer, and this is now my P-select. Okay. So the outer one is N-well, and then I have a P-select. Now I'll have to deposit an active layer. The active layer is here, the green one. So I draw this active layer inside this P-select. This is my active layer now, inside this P-select. All right. Now if I want to delete any layer, I'll simply again go back to this pointer option on the top. I'll click it and then I'll click on the layer which I wish to delete. So for example, I want to delete this green active layer, so I'll click on it and press the delete key on my keyboard, and it's gone. Okay. So again I want to draw, again I'll select the same box. Okay. Drawing tool, box, and then select active, and then I'll draw it. Okay. And then if I want to move this entire active region up or down, I can simply use my up or down arrows. Oh, not up and down arrows. I think control and plus up and down. Yeah, control and then up and down arrows. So it will move. Control and left and right. So this will move, right? So all these features are there. So with experience, you will learn all these features. Okay, so first step was N-well, and then a P-select, and then green one, that is active region. Okay. Now I'll use poly for defining the gate. So I'll just come to the center, maybe here, and I'll draw a poly line. So for drawing the poly line, you'll have to be very much careful about the dimension of the poly line. So it should be 2 lambda width, okay, not more than 2 lambda. So I just keep it to 2 lambda here. Okay. So again, lambda we specified in the previous lecture that how do you set this lambda is? So, yeah. So lambda is actually the spacing between the 2 dots, right? So that is lambda. Spacing between these 3 dots from here to here, that is 2 lambda. That is channel length, right? So currently, if you see my gate length or channel length, so that is 2 lambda, right? So minimum and even the maximum is permitted is 2 lambda, right? So this is 2 lambda, the channel length. Now the zooming also you can do by keyboard plus and minus buttons. So you just press the minus button, it will zoom down. Plus button, it will zoom. And then maybe you can use the mouse arrows on the keyboard to move this figure up and down. Right? So now I'll move this poly to the center. So since I'm drawing this arbitrarily, okay. So now this transistor is formed. Okay. So I can go to the extraction of this transistor. So there's an option to extract. So here that is, I think, file. Let us see, it's here, tools, extract. So if I do this, it will extract whatever is present in the layout. It will extract, right? So we'll extract later. Let us define the source and drain contacts. For source and drain contacts, you will utilize metal 1. So you draw a metal 1 over here, box over here. Okay, so maybe here, this one, and on the drain side also I draw a metal one box. Okay, and then to contact this active and this metal contact, so I'll use an active contact from here. Again, you will search here, there is an active contact here. So this is an active contact. I'll click on it and then I'll draw an active contact here. So for drawing a contact, you will have to again measure the contact size. The contact size cannot be, even lesser than or greater than 2 lambda by 2 lambda. The exact contact size is always 2 lambda by 2 lambda. And while drawing, you will notice that on the bottom of this tool window here, this one here, this time. So here you will find the dimensions of whatever quantity you are drawing. So it is showing here at the bottom W, that is width, height, and also the area. So whatever structure you are drawing, it will show its width, height, and area. And also you can check any of these polygons area or width or height by just clicking on them. So for example, I want to check the size of my end well, so I'll click on this end well here, and it shows that end well's width is 92.5 lambda, height is 45 lambda, and area is this much, 4162.5 lambda. Similarly, if I click on my P select, it shows my width is 73 lambda, height is 27.5, and area is this much. Similarly, my metal one, it shows some width and height. Okay, this one also some width and height, and then poly also. If I click on poly, you can see width is 2 lambda, right? So whenever poly is crossing the active, you cannot keep the width of the poly more than 2 lambda, because this defines my channel length, and channel length is the minimum size, feature size, which is 2 lambda is equal to channel length we had already specified some time back, right? And the height is also mentioned of this poly. Now I need to draw the contacts. I'll select this active contact and the box over here, and while I am drawing, you will also notice this palette which gives you the dimension, right? So I am drawing it here, and you will notice the size of this. Okay, so let me draw it here, 2 lambda by 2 lambda. So currently width is 2 lambda and height is 0.5. So I'll bring it down a little bit. So height is 1 now. So height is 2, width is 1. Now width I'll have to improve. Yeah, this is now 2 lambda by 2 lambda. Okay. Exact contact size. So I just keep it here as 2 lambda by 2 lambda. Similarly, I'll draw it here, and you can check it here, the dimension of this while drawing. So I'm drawing it here, and this is 2 lambda by 2 lambda. So I just stop it here, and maybe you can move this contact to the center if you wish by simply clicking on this contact and then control and up down arrows, or maybe left right arrows. Okay. Oh. I'll have to click this and then okay, anyhow. So my transistor is formed, that is PMOS is formed. PMOS transistor is now formed. Now let us extract it. So for extracting the parasitics of the transistor, and to see whether it's a transistor or not, I'll use this tool over here. I'll go to this tool window, tool tab, and then extract. Okay. So I just press this extract, click this extract option, and then it's asking me extract definition file, right? So I'll select an extract definition file from browse. Again, I go back to the same foundry, Moses, and then in Moses I select Morban 20. So I say that it's a 2 micron technology, let us say. So I'll select this Morban 20, double click, so Morban 20 is selected. Now it's also asking the spice extract output file. So let us say I want to name it as capital cell. Today is 13th October underscore 13th October. Okay. Or maybe cell underscore inverter, we want to make an inverter, let us say underscore 13th October, and wherever you want to save, you can save it. So let us say I want to save it on desktop. So I'll just press this save. And then what we want in output, so that also you have to select. So just press this tab output, and in output you can select the that you want to extract parasitic capacitances. So I'll select this option, that is I want to extract this nodal parasitic capacitances, that is source and drain capacitances. And there is an option that is ignore nodal parasitic capacitance less than 5 femtofarad. So let it be 5 femtofarads. So any capacitance which is less than 5 femtofarads will not be present in the extract definition file. The rest of the things are okay, and then you accept it, and again go back here, extract, and then you run it. Yeah, just press this run option. So once you do this, so it says layer, oh, there is some error. So let us see what it is. P base wire. Okay. Okay, maybe there is some error. So let us. Let me go back to the same slide. Okay, I think maybe we may have done some mistake. So we need an N well and then pre-select and then active. Okay, that is okay. I think this was N well and this is pre-select and this is okay. So before that, extracting, you need to also perform the DRC, that is design rule check, right? So which will check if there are any violations, then you'll have to correct them. Otherwise, if there are no violations, you will move to for extraction, right? So before extracting, let us perform the design rule check. Yeah? So this is again present here in the same tab, tools. You go to this DRC, design rule check, right? So just press this design rule check, and you press this OK then. So no DRC errors found because I kept everything big. And now let us try the extraction. So I say extract, same file, run. Oh, I think maybe before that, let us try to also replace setup by the same file, Morban 20. Where was it? Let me check. Desktop DIC design. So I'll go back to the same folder, Moses. Let me check where it is. So I select this Morban 20, that is 2 micrometer. I'm replacing setup. Let us see what happens. And then I perform DRC once again. No errors. And then I try to extract. Let us see. So let us keep things same and then run. Yeah, now it's working. Okay. So you have to replace the setup again. While extracting, you'll have to replace the setup so that the tool understands that you have, drawn a layout for 2 micron technology, right? So I'll just repeat that step once again. So now it's okay. And now it is asking whether you want to, there are no extraction of area or fringe capacitance for the layers. So let us say, okay, ignore. So area and fringe capacitances will not be extracted. Only the nodal capacitances will be extracted. Again, ignore. So ignore all warnings. In fact, you say ignore all. And let us go back to now the file where we have extracted the layout parasitics of the layout, right? So we had extracted it on the desktop. So let me go back to my desktop from here. Oh, where is it? Maybe let us try to extract once again. Tools, then go to extract, and let us extract it somewhere else. Maybe let me extract in C drive. C drive, let us say I'll edit. And here, save, run. Ignore all. I go back to C drive where I have extracted, and it has come here, right? This one. So I just open it in WordPad, open with WordPad. Yeah, so all this information you have extracted now. Okay, so extract date and time are mentioned, 13 October 2020 at 3:10. Then we are interested in what we had drawn. That is, we had drawn the PMOS transistor. Yeah? So layout of PMOS transistor we had drawn. So we can see this PMOS transistor. Okay, length we selected as 2 micron and width as 17 micron. So, so width you have already drawn it. So this width is coming from the same active. The width of this active. Okay, it's not seen here. It cannot be seen here, but yes, I'll show you later on. So PMOS we had drawn, and the drain gate source bulk nodes are also mentioned over here. And then important thing is these parasitics that we have obtained. Okay. So this parasitic 1 is present between node 1 and 0. That is drain and the bulk, or the drain and ground. So this is drain diffusion capacitance. Yeah. And this is source diffusion capacitance. So both are different because the MOSFET is not symmetrical, but you will draw symmetrical MOSFET by considering all dimensions, right? So this parasitic capacitance we have to extract, and then we want to use these parasitic capacitances in the SPICE simulations. So we'll try to draw a CMOS inverter using the same technique. So the same way we have drawn PMOS, we will also draw NMOS, and then we'll try to connect the gates of the two PMOSes and NMOSes and the drains of PMOS and NMOS and try to make an inverter. Right. So let us try to make an inverter. I'll go back again here and I'll say file new. Or maybe I'll close this window and I'll reopen everything. I'll say no. So let us go back to the same tool. So I open it. Okay. So let us try to redraw the PMOS, and then in the bottom of PMOS we'll draw NMOS, right? So for PMOS, again we will select N-well. So I'll select N-well from here. This is N-well. I have drawn now N-well. Let us draw. So this is, let us say, my N-well. And then inside N-well I draw this P-select. So I select P-select and then this P-select, right? So I'm keeping the dimensions large, as I said, so that there are no DRC errors. Then in the P-select, I need an active. So I select this active and I have drawn this active now. Right. Yes, so this is active mine. And then I cross this poly over the active. Okay, let us say poly is 2 by 2. So I'll watch out the dimension window where the width of poly is mentioned. So this is important. So I just keep it Now 2 by 2, sorry, width is 2, and then I put in the metal 1 contact over here. Similarly over here, okay. And then also I put an active contact here 2 by 2. So again I check the same dimension window. If it is 2 by 2, I stop, and then again 2 by 2 here. This is okay. So transistor is formed. Let us again perform DRC. Tools, DRC. So this is okay. No DRC errors found because everything is big. Now let us make a mistake here, right? Let us try to increase the dimension of this contact. So I'll delete this contact over here from here. So I'll select this contact first, and then I'll try to commit a design rule violation. Okay. So let me draw this contact which has a width or a size greater than 2 lambda by 2 lambda. Okay. Let us say this. So this is 3 lambda by 3 lambda. Okay. Now let me perform this DRC. I'll go back to tools, DRC. I say okay. So now it says 1 DRC error. Right. So you click on this, okay, and then you click on the layout. You will know where the DRC error, anywhere in the layout, maybe here, let us say, double click. Maybe I'll have to zoom it. Yeah, here. So it's saying that active contact exact size is not equal to 2 lambda. The error is active contact exact size is not equal to 2 lambda. So I'll have to fix this error, otherwise the transistor and their parasitics will not be extracted by the tool. So I'll go back again to maybe this. So I just clear error layer, right? So when I press this clear error layer, so all these errors are washed out, and I'll again try to redraw my contact. I'll delete the contact, and again I'll try to draw this contact. So this time I'll keep it 2 lambda by 2 lambda. Now this might be okay. Okay. Now again, if I try to perform the DRC, it says okay, no DRC errors found because I intentionally made mistake. Now let us create one more mistake. Let us try to extend this active, right? So let us try to make a mistake with this active, that is minimum spacing, here the surround rules, right? So let us try to violate this. So I am keeping it very close to my P select region, right? So this is spacing here between P select and active space, active. So there is some minimum design rule that is this spacing should be greater than something, right? So I'm trying to violate it. Okay. Now let us again perform a DRC, tools, DRC. Okay, so again it says 2 DRC errors found because one violation is towards the source side and other violation is towards the drain side. Okay, I click it here and it says that active to P select edge is less than 2 lambda. Okay, it is 0.5 and it is less than 2 lambda. So it should be at least 2 lambda, not less than 2 lambda. So this is spacing between the active and the P select edge, right? So it should be at least 2 lambda. Well, again, clear these errors, clear error layer, and again I'll try to delete this extra portion which I had drawn. So now it is okay, right? Again, I'll check DRC. Everything is okay now. Okay. Now let us draw a NMOS. So this is my PMOS, and now let us draw my NMOS. I'll again zoom and then back I'll zoom. So let me draw my NMOS at the bottom. Yeah, PMOS is present at the top, and now let me draw my NMOS at the bottom over here. So for NMOS, in a P-type substrate, I need a N select. So I'll select N select from here, then this box, and let me draw my N select here. So this is my N select. So inside N select, I need active. And then I need to cross the poly over the active. So I select poly and maybe from here itself, let us say. So poly is 2 lambda by 2 lambda. I'll have to again check that dimension window. It is W is 2. It's fine. I drop my poly over here, and then I need the metal contacts or the source and drain diffusion region contacts. I'm making everything big, as I said, because I don't want to make any errors, but this layout is not efficient, not optimum. So you please don't do the same thing. You have to first draw everything on paper, considering all dimensions, and then draw the layout. Okay. So W by H, I'll have to see it's 2 by 2. I'll drop it. You can also copy the same contact and then bring it here, over here by again saying Control C and Control V and then moving the contact by the arrows, or you can either draw. Okay, so I have drawn my contacts also. So my NMOS is present at the bottom over here. This one is my NMOS, okay? And this is my PMOS. Currently they are not connected, right? So now let us try to connect them. So for connecting, I'll simply extend the gates. I'll select this poly and connect the gates of both of these MOSFETs. Let me connect the gates. So the gates are connected now. Okay. Now the next thing is I want to connect the drains. Let us say these are the two drains of the two MOSFETs. So I'll connect these by simply selecting metal, and then from here I'll connect this metal line and bring it down. Okay. And simply I'll drop it over here. Maybe there may be some violation. Yeah, there could be some violations. Let us see. Maybe let me make this one bigger, or otherwise there may be some violations. So I'm making this big so that there are no violations. Yeah, okay. So I have connected the drains of the two MOSFETs, right? And now this, that is source of my PMOS. So this will go up and be connected to VDD. So let us say a VDD line is running over here, right? This is my VDD line running over here. And similarly, I will connect this source of my NMOS to the ground. So I'll say that maybe ground is running at the bottom. So generally the ground and VDD, they run at the top and bottom of the IC layout, right? So I have created a layout of my CMOS inverter, right? And now let us try to run a DRC on this, right? So since I have drawn everything big, so I may not see any DRC errors. So let us again run this DRC, design rule checker. So I just press OK, and there are no DRC errors found. Okay. And I showed how the DRC errors will come when you make a violation, right? So since I have drawn everything big, so obviously there are no violations, but you have to push the technology to limits. That is, first of all, draw everything on paper, set the dimensions of everything, minimum dimensions possible, and then draw the layout. Okay, so now let us replace the setup file, I mean this layout, by a setup file. So in fact, before that, let us save this layout as, maybe save as, let us say, file name CMOS inverter, October 13th. Let's say save, and then I perform I'll just replace the setup by the technology for which I want to export the parasitics. So I say file replace setup. Okay. Replace setup. And then I again go back to the same foundry Moses. So I go back to the same foundry Moses, and this Moses I select Morbin 20, that is 2 micron technology. So Morbin 20, 2 micron technology, and then I say okay. So once I do this, everything is gone, right? The color palette and everything has changed, so you may not see the layout properly. Okay, but don't worry. Now the next thing is you need to extract the parasitic. So I go back to tools, I press this extract. And again for extract definition, I select the same file, that is ext file, yeah, ext. Again in the same folder Moses, now we have extract definition file represented by .ext. So Morgan 20 for 2 micron technology, yeah? Extract definition. So I select this, open, and then where I want to save this CMOS inverter. So let us say Windows, this one here, and let me write here CMOS inverter, the name of the file, October 13th, new, and then I say save, and then I accept, and then again go back and say extract, and this time I run it. Okay, I say run. So the things are extracted, I hope. Let us go back and check that folder. So I'll go back to this folder and check. Oh no, where it was, in C drive. Let me go back to C drive here, this one. Yeah, this one, 13th October, this one. So I again open this in the same WordPad, open with WordPad. Yeah, so this time I see in my extract definition file, I see that I have now two PMOSes, right, present. So I have two PMOSes here. One is PMOS and the other one is NMOS, right? And the connections also you can notice, drain, gate, source, bulb, and the drains of the two MOSFETs are shorted here. You can check. The drain is 3 for PMOS and drain is 3 for NMOS also. The drains are shorted and gates are also shorted. Gate is 6, right? Drain, gate, source, bulb. So gate is 6, PMOS and NMOS. Source, which will be connected to VDD, and source will, this one will be connected to ground. And these are bulb connections, 5 and 4. Okay. And the length, channel length is 2 micron, because we had replaced the setup with 2 micron technology. So channel length, if it is, I mean, we had drawn 2 lambda, we had not drawn 2 microns, but you draw 2 lambda and select the process technology file as 2 microns, so the final channel length will always be 2 microns. So if you select the process technology as 0.5 micron, the channel length will be here 0.5 micron. Similarly, width of the MOSFET, so that comes out to be somewhere around 15 microns. So we'll verify this width very soon. And the width of NMOS is 21.5 microns. Similarly, area of the drain, perimeter of the drain, area of the source, perimeter of the source. How to calculate this from the layout, I'll just tell you. Okay. And let us go back to, oh, we didn't extracted the parasitics capacitances. So we have to extract them also. So let us go back to our this thing layout, and again let us try to extract the parasitics. I'll close this, and for parasitics you have to select this output option, and here you have to check this right nodal parasitic capacitances. Unless you select this, you will not see any parasitics. Okay, and then you say run, replace existing, yes, and then say ignore all. Then I go back again to the same file here, we refresh it and open it. So this time let us check. Yeah, so this time parasitic capacitances are there here. So parasitic 1, 3 parasitic capacitances it has obtained. So this is between 1 and 0. Okay. So 1 is source of my NMOS, right? Drain, gate, source. So this is source of NMOS. So that means this is source diffusion region capacitance of my NMOS. Similarly, parasitic 2 is connected between 2, 0. So 2 is here, that is source of my PMOS. So this is source diffusion region capacitance of my PMOS. Similarly, this parasitic is connected between 3 and 0. And 3 is the drain of the two MOSFET. That is the drain diffusion capacitances of both PMOS and NMOS combined together, right? So So that is somewhere around 200 femtofarads. Okay, so three capacitances are mentioned over here. One is appearing at the drains of the two MOSFETs, the combined value, and the other two are at the sources of my PMOS and NMOSes, right? So these capacitances, you will utilize them in your SPICE, circuit simulation. Okay. Now let us go back to our assignment. So there is one more new assignment coming up based on this. Yeah. So this is assignment number 3, and here you will draw the layout of CMOS inverter. So full adder you will not do now, we'll do it later, but you will draw the layout of CMOS inverter only, not full adder. Full adder we will draw later. So layout of CMOS inverter of assignment 1. So assignment 1 we had some CMOS inverter where the width and channel length of PMOS and NMOS were mentioned. So using the same width and length of PMOS and NMOS, you will draw the layout of CMOS inverter, okay, using the lambda rules. Okay. And the layout shall consume minimum silicon area, okay, and use 2 micron technology, that is channel length is 2 microns. Second step is to extract the parasitic capacitances. Okay. And then third is to find the propagation delay, noise margin, and fan out of the gate in presence of these parasitics. That is the 3 capacitances that you will obtain: source and drain diffusion region capacitances. So those capacitances you will include in your SPICE simulation of the first assignment, right? And then find out again the propagation delay, noise margin, and fan out of the gate in presence of these parasitics. Okay. So now let us come back to the same inverter layout. In fact, let me close this once again here, and I'll open this again. And then let us try to find out the area. Okay, so let us try to find out the area of or the width of PMOS and NMOSes, and also the area. So I'll open the previous CMOS inverter here. This one we had drawn. So I'll open it. I had saved it, so I can open it. Now let us verify the width of my PMOS and the area of my PMOS, right? So the area of PMOS or any MOSFET, you will see that, let us say, we say source area, and let us say this is my source and this is my drain, right? So obviously source and drain area seems different. So for finding the source area, when this source area will be in this active region, right? That is towards the left of my poly, the green region which you see, so that specifies my source area, right? The source area, for calculating source area, you will simply measure this dimension and multiply with this dimension, that is the width of my PMOS, right? So my width of PMOS is from this point to this point, okay? This width of my PMOS is from here to here. So let us measure the width of this PMOS. Okay. And again zoom it a little bit more, and let us try to measure the width of PMOS. Okay. In fact, if I click over here, I can see at the bottom the dimensions. Width is 45. Height is 15. So this may be 15 lambda. Let us count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 15. So this is 15, which is saying H. That is actually the width of my transistor. That is PMOS's width is 15 lambda. Okay. Let us verify in our SPICE that we had extracted. So we had extracted in here. So I go back to open with WordPad. Yeah, so PMOS's width is 15 microns. Okay, and this is in 2 micron technology. Yeah, so 2 lambda is 2 micron, so lambda is 1 micron, right? So 2 lambda is L, that is, and L is 2 micron, so lambda is 1 micron. So the width is here, so this width is 15 micron, okay, or 15 lambda, right? Because lambda is 1 micron, 2 lambda is equal to channel length is 2 micron, right? So this channel length is 2 micron, so lambda is 1 micron, so that means this is 15 lambda width here, which is showing here height. This is actually width. If width is 15 lambda, that is 15 micron, which is present in my SPICE netlist also, right? I can verify here. Length is 2 micron, okay, no issues. Then drain area, okay, so the drain area it says is 367.5. Drain area is 367.5 picometers. Instead of micrometer, I think it's saying picometer. P stands for pico. And the perimeter of drain is 79 microns. So let us try to find out the perimeter of drain first of all. So perimeter of drain will, that is, let us say this is, let me check first of all which one is big here. Then we can identify. Okay, correct. Yeah. So the drain is on this side. Okay, this is my drain here. Okay. And the perimeter of drain will be calculated by measuring this side, okay, and this side, right? So you add up these 3 dimensions, that is from here to here, and from here to here, and then from here to here. Okay. Now this dimension is not added in calculating the parameter, that is the dimension which is towards the gate. So that is not considered while calculating the perimeter of the drain or source region. So only 3 dimensions, that is this dimensions plus this dimension and plus this dimension. So let us see what are they. So from here, if I start counting, in fact I don't need to count, I'll simply keep my pointer over here and look at this dimension over here, right? So this is currently maybe let us select something. It's not moving. Or maybe we can count. We don't need to count. I think it will directly come on. Maybe let us try to draw something here. Let us say this one and just check the dimensions. So it says in the dimension window, it says width is 24.5. So the bottom of this layout editor, you will see that the dimension window says that width is 24.5. Okay. If I extend, it goes further, right? So, but we have to only consider this. So 24.5. So 2 times 24.5. Yeah. 24.5. Delete it. I don't want to keep it. So 24.5 is this one, and 24.5 from bottom also. So this is 49, that means, right? 24.5 plus 24.5, that is 49. And this width is 15. That's the width of my PMOS is 15 micron. So 49 plus 15. So how much it is?
64.
49 plus 15 is 64. Is it so?
Yes, sir.
Okay, 64, that means should be my perimeter of the drain. Let us verify. Oh, it is 79. Is this
So we have to calculate on other side also, so other length plus 15 again.
Oh, then 64 plus 15. Yeah, correct. So 64 plus 15 also we have to do. So then it is 79. Correct. So this was 64 and plus 15 also you have to consider. So that way perimeter is calculated. 64 plus 15 is 79. Okay, this tool calculates it this way. So that is okay. But I think in our textbook you will find that the side towards the gate is not taken into consideration while calculating the drain perimeter. But okay, the tool takes it this way, so let us take this way. So perimeter of drain is 79. So similarly, you can find out the perimeter of source also. Okay.
Tools also take from the gate side also.
So in this tool, it is being taken from the gate side also. But generally, I think in the textbook, in this course, you will find that later on that it is not considered towards the gate side for calculating the perimeter. Okay. But yes, in this tool, it is taken as that way, right? So it depends upon the model, how you model your things. Now the drain area also can be calculated similarly. So let us try to locate the drain area from here. So this is my drain. So for drain, obviously I'll have to simply multiply 24.5 by 15, right? So 24.5 multiplied by 15 is how much? So let us take a calculator over here. 24.5 multiplied by 15. So that is 367.5. So it is 367.5. Okay. So similarly, source area can be checked. Let us see the source area. This side is source. And for source also, knowing the width of the source, I'll again consider this line over here. The width of this line is 18.5. So 18.5 multiplied by 15, that means. Okay. So let me delete this. So 18.5 multiplied by 15. So let me say 18.5 multiplied by 15. That is 277.5 is the source area. So let us check. Source area, where is it? This one.
Yes.
Yeah, this one. So this is 277.5, correct. 277.5 it is coming, right? So 277.5. So similarly, you can also find out the perimeter of the source, and the same numbers you can find, that is drain area, source area, perimeter of the drain, and so perimeter of the source for NMOS also. Okay. Now these are very important, yeah, these areas, because these actually define your parasitics. These values are dependent on these areas. So if you try to minimize this area, these values will also change. Right? So one has to optimize their devices so that the parasitic requirement is met as per the requirement for the performance metrics. Whatever performance metrics suggest. So depending upon our performance metrics, one has to modify the width. Yeah, depending on the width. I mean, this is controlling actually the drain area and source area. Width. Okay. So I think I'm done with today's lecture. If you have any questions, then maybe you can ask. And the aim of this lecture was to, generate a knowledge of, how to create these layouts, and then how to extract the parasitics from the layout, and then how to use these parasitics in the SPICE simulation to see the effect of the parasitics on the actual performance of the inverter. Right? So earlier we did not consider these parasitics, but now depending upon the layout size, the parasitics will also vary, and depending on your parasitics, your inverter performance will also, or any digital circuits performance will vary depending on how you draw the layout and how the how much parasitics you are obtaining from the layout. So if you have any questions, then maybe you can ask. Otherwise, let us end this class here itself.
Hello, sir.
Yeah, please.
Sir, can you say show the assignment? Third assignment. 1 second.
Can you please repeat once again?
Yes, sir. Assignment, sir.
Assignment. Okay. So assignment is that you have to draw the layout of the same CMOS inverter that you had simulated in assignment number 1. Right?
Okay.
So assignment
Okay,
number
sir.
1. Yeah. So PMOS and NMOS width were given. So considering those PMOS and NMOS width, and the channel length is 2 micron. So there also we had used 2 micron as channel length. So you have to draw the layout of this CMOS inverter and extract the parasitics, capacitances, and then include them, that is include these parasitic capacitances into your SPICE circuit simulation file, and then simulate the inverter behavior and find out the propagation delay, noise margin, and fan out of the gate in presence of these parasitics.
Okay, sir. Thank you.
Anything else?
Hello, sir. What about the submission date of this assignment?
Yeah, let us fix the submission date. So today is 13th October. The previous assignment had the submission date of, I think,
20th.
20th October, sir.
Okay, 20. So let us take it as 27th,
Okay, so
1 week after.
Mid-sem exams हैं sir.
Mid-sem exams
When are they? Mid-sem exams?
26, 27, 28.
Okay. So, okay, let me check 26, 27, and 28. Okay, so maybe let us say then Monday, 2nd November. Monday. Okay. So 26, 7, 8, you have midterm exam, and let's say 2nd November then. So I'll keep it 2nd November. 2nd November. Let's say 2nd November. Right. Submission date is 2nd November. Anything else?
Hello.
Yeah, please. Please.
Sir, we haven't connected the VDD and ground points in the tool. So is this tool automatically understand that these are the VDD and this is ground?
You need to specify VDD and ground. So there is an option of mentioning, VDD and ground lines. You can write the node names as well. But, for now, I think that is not required. So let us not make things complex now itself. Let us try to make things simple and, utilize the minimum, possible things so that we can, simulate this inverter, right? This assignment. Later on, you can explore this tool. There are many more options available, right?
Thank you, sir.
Yeah.
हेलो
Yeah, please.
सर मुझे वो पैरासिटिक कैपेसिटेंस आपने जो वर्ड पैड में देखकर समझाया मेरे को थोड़ा समझ में नहीं आया.
Okay. So these parasitics, you need to extract them. You can check. I'll just upload my video. The lecture.
No, I just want to know how do you read them, like para 10 ये कौन सा कैपेसिटेंस है? DS वाला है?
Right, correct. So you will have to identify the nodes. So for example, for this parasitic, that is parasitic 1, CPAR 1. So the nodes are positive is 1 and the negative node is 0, right? So 1 and 0 you will locate in the MOSFET here. So 1 is present in NMOS, okay? And the NMOS is connected, any MOSFET is connected in this form, that is drain gate source bulb. That is 3 is drain by, okay, here 3 is drain, 6 is gate, 1 is source, and 4 is bulk. Okay, these are node names. So 1 is, that means source here for NMOS, which is present over here. So that means it is appearing at the source of my NMOS. So that means it is source diffusion capacitance.
Okay.
So similarly, 2 is appearing in PMOS, source. So that means it is associated with source of my PMOS. Similarly, 3 is appearing at the drain.
Both,
okay?
sir, both.
Yeah, drain of both the MOSFETs. So that is, it is the sum of the two drain diffusion capacitances of NMOS and PMOS.
Correct. Right. Thank you so much.
Anything else?
sir, is this parasitic capacitance is the responsible for the propagation delay of
Yeah,
the...
definitely. Correct. So TPLH and TPHL are dependent on the parasitics.
And also here we are, there is one observation, sir. As we increase the width of the PMOS, then the TPLHs keep on decreasing. And how we can know the parasitic capacitance based on the widths?
Yeah, so that calculation we have to understand, and later in the course we will understand how to calculate these parasitics from the MOSFET, right? So that will be covered in the later part of this course. Maybe after 2-3 lectures you will see that.
Okay, sir.
Yeah. Anything else?
Sir, when you will provide this software?
So please create a WhatsApp group. I'll maybe post that software in the WhatsApp group. Yeah, add me also to that WhatsApp
There
group.
is, sir, there is a WhatsApp group for SSD, sir. We can add
Yeah,
you to in that group.
or maybe you can create a separate group for this course, and then add me into that group. So because it is not good to use the same group for all courses.
Sir, but we don't have your number.
So yeah, please take it. I'll maybe email it. In fact, in my emails it might be mentioned. So whatever emails you get from me, so the number is mentioned. Though I'll again send you an email with my number, right?
So write in the chat box here.
Or maybe I'll write it here. So maybe. Okay. So please add me there. So I'll share this tool with you. Or otherwise, you can also download the same tool from the web. Yeah, please.
Sir, how we define the lambda? Like you were saying, the spacing is 2 lambda by 2 lambda. What does this lambda stand for? Like 2 micron is equals to 2 lambda.
No, 2 lambda is channel length, right? So if the channel length is, let us say, 10 microns.
Yes, sir.
So 2 lambda is equal to 10 micron. That is, lambda is 5 microns.
Okay, sir. Sir, basically lambda, what is the basic unit lambda?
Lambda is, in the tool, you will see these grid lines, yeah, these dots. So between these two dots, the spacing is lambda. So from here to here, this is lambda by lambda. Okay. Between these two grid lines, so this is lambda.
Okay, sir. Thank you.
Anything else? So if you have no questions, then let us end the class, and we'll meet day after tomorrow.